Hello everyone. Let's talk about something that sounds like it came straight out of a science fiction movie, but I assure you it's very, very real. It's called quantum entanglement. Now the word quantum just refers to the tiniest, most fundamental level of our universe. We're talking about the little bits and pieces that make up everything, like electrons and photons. Entanglement is a special, mysterious connection that can happen between these tiny particles. Imagine you have two of these particles, and they become linked in a very particular way. From that moment on, they act like a single team no matter how far apart they get. It's a connection that works instantly, faster than the speed of light. Think of it like having a pair of magic gloves. When you create them, you know that one is for the left hand and one is for the right hand, but you don't know which is which until you look. You put them into two separate boxes and mail one box to your friend on the other side of the planet. The moment your friend opens their box and sees they have the left glove, you instantly know, without even looking, that you have the right glove. Quantum entanglement is a bit like that, but with a much deeper and stranger kind of connection. The particles don't have their properties set in stone. They decide them the moment one is observed. This incredible link is at the heart of quantum mechanics, the set of rules that governs the world of the very small. Unlike the physics we see in our everyday lives, where a ball is either here or there, the quantum world is all about possibilities. A particle can be in many states at once until you measure it. When two particles are entangled, their possibilities become linked together. If one particle chooses to be in one state, its partner instantly chooses the opposite state. This happens whether they are in the same laboratory or in different galaxies, which is a truly mind-boggling idea to consider. So, to put it simply, quantum entanglement is a special bond between two or more tiny particles. When they are entangled, measuring a property of one particle, like its spin, which you can think of as it pointing up or down, instantaneously influences the property of the other particle. It's a guaranteed instant correlation. This isn't like finding out a secret. It's like the particles are communicating with each other in a way that we don't fully understand yet. It's one of the biggest, most exciting mysteries in all of science, and exploring it changes how we see the universe itself. The idea of quantum entanglement made some of the smartest people in history scratch their heads in disbelief. The great Albert Einstein, a scientist whose work changed the world, was very skeptical about it. He famously called it spooky action at a distance. He just couldn't accept that two objects could affect each other instantly over vast distances. It seemed to violate a fundamental rule of the universe that he helped establish: nothing can travel faster than the speed of light. How could information get from one particle to another in no time at all? It felt like magic, not science to him. Let's use a simple story to understand his point of view. Imagine a magician gives you and a friend each a special coin. These coins are linked. The magician tells you that when you flip them, if one lands on heads, the other will always land on tails, and vice versa. You and your friend travel to opposite ends of a very long street. You both flip your coins at the exact same time. You get heads. Instantly, you know your friend's coin must be tails. Einstein thought this was how entanglement worked. The outcome was already decided from the start, like a secret plan hidden inside the coins. He believed there had to be some hidden variables, or secret instructions, that the particles carried with them from the moment they were created. In our coin example, this would be like one coin having a hidden instruction that says, "I will be heads," and the other having one that says, "I will be tails." This way, there's no spooky communication needed. The outcome was predetermined all along, and we just didn't know it until we looked. This would preserve the rule that information can't travel faster than light. It seemed like a much more sensible, logical explanation for this bizarre phenomenon. However, Einstein's idea of hidden instructions was just one side of a huge debate that lasted for decades. Another brilliant physicist, Niels Bohr, argued that Einstein was wrong. Bohr believed the quantum world was genuinely weird. He said the particles don't have predetermined properties. Their states are truly undecided until the very moment of measurement. The spookiness, he argued, was real. This disagreement between two of the greatest minds in physics set the stage for experiments that would eventually try to figure out who was right about the fundamental nature of our reality. For a long time, the debate between Einstein's hidden instructions and Bohr's inherent weirdness was just a philosophical argument. There was no way to test it. Then, A physicist named John Bell came along in the 1960s and changed everything. He devised a brilliant mathematical test, now called Bell's theorem, that could experimentally check if those hidden variables Einstein talked about could actually exist. His theorem set up a game that quantum mechanics and classical physics would play, and the results would show which one described reality correctly. It was a showdown for the soul of physics. The experiments based on Bell's theorem have been performed many times since then, with incredible precision. And every single time, the results have been the same. The universe, it turns out, is even stranger than Einstein was comfortable with. The experiments proved that there are no hidden instructions. The particles do not decide their states ahead of time. The connection is real, and it is instantaneous. Niels Bohr was right. The spooky action at a distance is a genuine feature of our universe. The world of the very small really doesn't play by the rules we're used to. This is what makes entanglement so profoundly different from our everyday experience. In our world, things have definite properties. A car is red, a ball is round, a book is on the table. We assume that these properties exist even when we are not looking. But in the quantum realm, properties like a particle's spin or position can be genuinely fuzzy and undefined. It's only when we interact with a particle, when we measure it, that it chooses a definite state. For entangled particles, this choice by one particle instantly forces the other into a corresponding state, breaking our classical intuition. So, the magic coin analogy we used earlier isn't quite right. A better analogy would be two shimmering coins that are neither heads nor tails, but exist in a ghostly state of both at once. The moment you look at your coin and it settles on heads, its partner, even a galaxy away, instantly stops shimmering and settles on tails. It wasn't secretly tails all along. Your act of looking at your coin caused it to become tails. That's the true mind-bending weirdness of quantum entanglement. It challenges our very understanding of space, time, and reality. You might be thinking, okay, this is weird and cool, but what does it have to do with me? Well, this spooky action is not just a scientific curiosity. It's the foundation for a whole new generation of technology that could change our world. Scientists and engineers are learning how to harness the power of entanglement to do incredible things. One of the most exciting areas is quantum computing. Regular computers use bits, which are either a 0 or a 1. But a quantum computer uses qubits, which thanks to quantum mechanics, can be a 0, a 1, or both at the same time. By linking these qubits together through entanglement, quantum computers can explore a vast number of possibilities all at once. This could allow them to solve incredibly complex problems that would take today's best supercomputers billions of years to crack. Imagine designing new medicines by simulating molecules with perfect accuracy, creating new materials with amazing properties, or developing powerful artificial intelligence. Quantum computing, powered by entanglement, holds the key to unlocking these breakthroughs and solving some of humanity's biggest challenges in medicine, climate science, and more. Entanglement is also revolutionizing the field of cybersecurity. Today, our secret information is protected by mathematical problems that are hard to solve. But a powerful quantum computer could potentially break these codes. The good news is that entanglement offers a solution: quantum cryptography. By sending information encoded in entangled particles, you can create a communication channel that is perfectly secure. If a spy tries to intercept the message, the very act of observing the particles would disturb the entanglement, and both the sender and receiver would know instantly that someone was listening in. It's like having a cosmic burglar alarm. From a spooky puzzle that baffled the greatest scientific minds, quantum entanglement has become a spectacular tool for innovation. It reminds us that the universe is full of mysteries, and by exploring them, we can discover new rules and new possibilities. What was once seen as a flaw in a theory is now seen as one of its most powerful features. The ongoing study of entanglement continues to push the boundaries of what we know and what we can do, promising a future where the strangest aspects of reality power our most advanced technologies. Science is cool,